Good morning, everyone. Not quite sure how I'm going to follow up on those cool animals. So I don't have anything to say about wildebeest and so on, but I am going to address the task of collective intelligence, and specifically I have an engineering mindset. So I am really interested in how do we actually create these kinds of systems. What I want to do is talk about that high-level direction at the beginning, and I'm going to go into details on two specific things. One is about self-optimizing workflows, and then how to get the individuals in a workflow to productively argue with each other. So my model of a collective intelligence is a sort of system of people and AI agents that are talking to each other, working together, and I'll call the way that they're connected together and the rules and patterns that bind them together to be the workflow. And so the task I'm really interested in is how do we create these mixed teams, combined of people and machines, and how do we actually get them going and how do we make them work effectively? So I'm going to take a simple model because there's lots of ways of thinking about this. The first is I'm going to assume that there's some intelligence, say a person who's actually got some purpose in mind. So they have their objective and they're going to create this initial workflow that combines people and agents together. And then I'm going to look at how we can actually improve that workflow over time. In particular, one, by having the crowd make the workflow work better. Two, by using algorithms to make the workflow work better. Okay, so recasting the problem is self-optimizing workflows. And I'm going to start by looking at the instructions in the workflow. And why am I so focused on the instructions? Well, it comes out of a completely different research project I had, because I also study natural language processing, and we're interested in taking large corpus of web text and trying to extract information from it. And my student, Angli Liu, and I had an idea that maybe what we could do is we could train these information extraction systems using a combination of training data for the machine learning algorithm, where some of the data is automatically generated using something called distance supervision. And this is great because we get lots of data, but it's noisy. And then we would also use crowdsourced data, which would be very high quality, but we wouldn't have as much of it. But we combine these two things together, and we should come up with a much better information extraction system. So we were really excited about this. And then, unfortunately, we looked and other people had already had this idea. And so there had already been 3 publications talking about it. So that was really a bummer for us. But the weird thing was it actually didn't work. I mean, the idea is such a good idea. It really seems like it should work, and yet it didn't work. And so we dug into it a little bit and eventually published a paper, had all sorts of cool graphs and things. But the bottom line was the reason why it didn't work is because their crowdsourced workers actually generated data that was just as noisy as the automatic heuristic. So their crowdsourced workers were doing a terrible, terrible job. And we looked to try to figure out better why that was, and came up with a couple simple lessons. So the first lesson was the workers don't read the instructions. And that's actually pretty intuitive. If you think about people on Mechanical Turk, they're in a hurry and so on. So one thing you need to do if you're actually building these kinds of systems is force them to read the instructions. So divide the instructions into little pieces and then give them little quizzes to make sure they really actually paid attention to it. Then the second point is, actually most of the instructions are really terrible and they're very confusing. They seem obvious to the requester, but people don't understand them. So what you need to do is you need to polish them, to go out there, see whether workers understand them, if not, revise them. And you do this over and over and over again, and it works. And if you do that, you get great results, but it's a pain in the neck. Nevertheless, it's really important. So we tried to think about whether or not there's a way of making this whole process simpler. In particular, can we get the instructions so that they improve themselves? So this is the PhD thesis of Jonathan Bragg, co-advised by my colleague Mossam. So again, this is what I think best practice does, is we create a set of instructions and we give them to workers and we evaluate to see whether or not they're actually doing a good job, and you go back, you modify the instructions, and eventually once you get them into a good situation, you actually have the workers do the work. And so what Jonathan's proposing is a meta workflow. So it combines both the actual workers and the requester. All of them are doing microtasks as part of this workflow. So we're sort of wrapping this inner circle with another set of processes where we try to figure out what's wrong with the workflow and improve it, especially with the instructions. So what can go wrong with instructions? Suppose we're trying to do image labeling. We've got a whole bunch of images and we want to build a classifier that recognizes birds. So we ask workers, here's a picture, mark whether or not it has a bird. What could possibly be confusing about those instructions? Well, in this case, it's pretty obvious. But then after a couple hundred pictures, you get this picture, and should I really mark that as a bird or not? It's very confusing. What about that? Is that a bird? So these are the kinds of things that cause problems in your workflow, and you don't think about them, and it's really only after you've gone through hundreds of examples that they actually come up. So what we want to do is have the workers help us figure out these problems. So instead of having them answer yes or no, we just give them a slider, and they can basically say, yes, this is clearly a bird, this is clearly not a bird. And then there's this gray zone in between. This actually ties in very closely with Chris Welty's talk yesterday, where it turns out there's just lots of ambiguity, although we have a different approach to how we should deal with that. Then if somebody marks, yeah, I don't know whether these tattoos of a bird should be marked as a bird, then they have another task, which is to try to explain, and the wording here is actually really important, try to explain why some other worker might be confused about this example. So they might say tattoos might be unclear because I don't know whether illustrations of birds should count as birds. And then after we get a number of these, we use a clustering algorithm based on the descriptions to try to figure out what the possible confusions are. And it turns out you can find most of the confusions by asking a relatively small number of workers on a set of examples, and you can do this adaptively. And then we have an interface which allows the requester to actually start making this whole thing better using what their high-level end goal is. So the requester's interface has a set of these clusters about confusions, and then it has a panel on the right-hand side which allows them to fix things. So what they can do is they can revise the instructions by writing in, no, I don't want you to count food as a bird, and so on. And furthermore, you can drag and drop and put in examples that get automatically inserted into the instructions to make it very clear to the workers. And then finally, you can also drag other examples down into a panel which is going to create little tests that will make sure that the workers actually read the instructions. And then you click off and you sort of move through all of the confusions until you think you have the workflow in a much better place. And then the system goes out and it reruns the new instructions on a new set of workers, specifically sampling from the different confusions as well as the original images to make sure that you're doing better. And you can iterate this process, but you can do it much, much faster. So that's the process Jonathan's is working on now. We hope to have results on how much that improves things shortly. And then finally, that's a way of having the workers help improve the workflow. But we've also done a lot of work on having AI algorithms improve the workflow. So workflow optimization. And the basic idea here is to think about the system as an intelligent controller where the computer's trying to figure out which jobs to suggest to which people. And we and other researchers, like HA, for example, have looked at a number of different have applied this general idea to a number of different processes. I'm going to give you one example of adaptive testing. So it turns out that, since workers make mistakes, oftentimes what people do to make sure that the workers are actually paying attention and knowing what they're doing is put in test questions along the way. Those are called gold questions because we know the answer to those. And people have adopted this practice, but there's sort of a key question. What percentage of gold questions should we insert, and what's the threshold for a passing grade? And if you look at the various approaches, there's wide disagreement about what you should use for those parameter values. And in fact, every static policy you can come up with, there is no right answer for those parameter values because the workers change, and they change over time, non-stationary population, so you really want to have the system be adaptive as it figures out whether it's getting a good job. So just the architecture we built is basically the requester can specify a base policy, which might be like put in 20% gold questions and tell people they're not doing a good enough job if they're less than 80% right. And then we learn a much better policy called a POMDP policy I'll talk about more in a minute. So the system basically chooses between, in this case, just 3 actions. Should I test a worker? Should I ask the worker to get really work done? Or should I tell the worker that they're not doing a good enough job? And then the observations coming back are basically, if it's a work question, you don't learn anything. But if it's a test question, you can see whether they're doing a good job. Of course, you don't want to do too many test questions because you're not getting work done. So we model this as a partially observable Markov decision process. So the system has a belief state about the quality of the workers. It has a set of actions. Each one has a cost. So it could be the amount you're paying a worker. And it gets an observation which lets us update this belief distribution after every action. And these models have been used in robotics all the time with, for example, sonar systems as the observation model. But what we're doing is having the responses that are coming back from Mechanical Turk be the observations from our actions. And what we're trying to do is come up with this policy, which is a mapping that says what action should the controller perform in this situation. And we want to do it as we're actually learning these probability models and learning the reward model as we go. So it's a reinforcement learning problem. As such, it's governed by Bellman's equation. We're using model-based reinforcement learning. We're using this base policy, like test 20% of the time, as the exploration model, and then we gradually shift over into an exploitation model as the system goes on. And here's an example. Even starting with really quite a good baseline, the system, after a little bit of time, manages to be quite a bit more efficient as it goes on. So this is one example of using reinforcement learning and a partially observable Markov decision process to automatically optimize the workflow as it proceeds. And one can apply this approach to many other cases. So the final part of my talk is about getting workers to argue with each other. So why would you want to get workers to argue? Well, again, to get high accuracy, oftentimes what requesters do is they give the same task to multiple workers. And so then the question is, how do you actually aggregate the results? So one thing you can do is you can do majority vote, and that works pretty well. You can also use expectation maximization to learn to estimate the accuracy of the workers, and then use basically an accuracy-weighted majority vote. And all of those systems work really well if the problems are pretty easy. But if the problems are hard, in particular, if the problems are so hard that more than half of the workers are going to get it wrong, then these approaches just get it even more wrong because they amplify that error. And instead of putting the workers into different boxes and having them not talk to each other and just aggregate results with vote, why not have them actually have a discussion with each other? That's what we tried to do, and we tried to do it on this task. Again, it's a natural language task. So we're trying to recognize whether or not a particular relation holds, very much the same task that Chris Welty was talking about. So here, from this sentence, not knowing anything about Bush and the United States, can we conclude that Bush lives in the United States? Based on a bunch of reasonably complicated guidelines that people in the text analytic conference have figured out this is what it means to deduce somebody lives there. It's actually surprisingly hard to make these judgments. It's so hard, right? You just guess randomly, you should get it 50% of the time. Majority vote gets it right only 59% of the time. And with EM, you get up to 65% of the time. That's like a terrible, terrible score. So clearly voting doesn't give us the results we want. So why not have them discuss with each other? So this is basically taking the idea of talk pages in Wikipedia and trying to collapse it down to this micro-task workflow idea. What we do is we come up with 3 tasks. First one is an assess task, so does lived in hold yes or no? Then there's a new one which basically says write a reason why you think your answer is right. And then finally, there's a reconsider task where you get paired up with another worker who had the opposite opinion, look at their justification, decide if you should change your mind or not. So here's the workflow. First worker goes through, they're asked to answer a question, they say it's false. So then they're asked to write a justification, and they write some tests. Here they're saying, we know that this person lives in Thailand, but we can't conclude whether they live in Bangkok. Another worker comes through, they think it's true, they write a justification, and now we combine those two together, and worker 2 sees worker 1's results and maybe changes his mind. So what we hope was going to happen was you'd have this one person out there who has the right answer, manages to convince all of the people in red that they got the wrong answer, and we get much, much higher results. Unfortunately, when we did it, what we found was that the people with the wrong answer convinced the right answer folks to change their mind. It was quite depressing. Luckily, we came up with another qualification. So looking at the kinds of justifications that people wrote, we applied the Flesch-Kincaid test to see basically how sophisticated was just the quality of their writing in their justification. And our hope was that by picking people who can write sophisticated justifications, maybe they'll be able to read and understand other people's justifications in a better manner. So basically what we're trying to do is, get rid of the people who are bozos. And in fact, that really did the trick. So you get 65% accuracy with EM. You get 71% with MicroTalk, and then if you filter for discerning workers and use EM, we get up to 84%, which is really quite a good rate for this very hard task. Since then, we've done a bunch of other things. That's just choosing random arguments, but if you choose the best argument, then we can do even better, and we had a number of techniques that let us pick good arguments that are persuasive. The other thing is the arguments that we were showing people up until now were just arbitrary arguments, and really it'd be good if the counter-argument was specific to a person's justification. So here we came up with a real-time crowdsourcing approach where we paired people up, gave them sort of a chat interface where they could talk back and forth, actually rebutting each other's points until they came to a decision, and then afterwards, had them edit and revise their justifications, and we're doing experiments on that now. Okay, so in summary, what I'm really excited about is coming up with tools that allow us to create these kinds of collective intelligence systems. Given some sort of high-level objective, how do we figure out the right way to combine people and AI systems to come up with high-quality results? I agree that instructions are a key part of the process, and we can use the crowd to improve those, and that POM-DPs and reinforcement learning can be used to automatically augment and improve the workflow. And then finally, talked about going beyond EM and majority vote to a discussion-based system where people don't spend too much time arguing, but they're able to hopefully improve their results going forward. There's lots of related work which I have to talk about, but I'm a little bit over time, so maybe I'll defer that to the question session if people are interested. And let me thank my many collaborators and the people who funded this work. Thank you. Yeah.
Kind of unfair for me to ask because I'm doing similar things, but I think one of the interesting places where we diverge that's worth discussing is what would you consider the right guideline to give the workers in the case of the tattoo of a bird? Do you modify the guidelines to say yes, that is a bird market as such, or don't consider artwork or something like that?
Yeah, that's a great question. And as Chris pointed out, one of the challenges of these things is the guidelines can become longer and longer and more complicated. For some of the NLP guidelines, they stretch into like 30 pages long of detailed descriptions about what you should decide here versus there. So I think it's a problem when the guidelines get too long and complicated. The actual decision depends on why are we labeling this data in the first place. And that's why we involve the requester in the loop. So they're the one who actually has to make that decision. It depends on, if they're building something which is going to be, I don't know, a quadcopter that goes out and forages hunting for birds, then obviously the answer would be no, tattoos shouldn't be birds, nor should already cooked birds. So it depends on what your high-level objective is, and so that's why I think the person. And some things maybe they don't care. Yes.
The same way that the image recognition community really benefited from ImageNet, are there areas where training data would have a big impact on the field of NLP, where there is currently not training data available at a quality and scale that is needed for advances in NLP?
I believe absolutely. So the machine learning algorithms, especially the deep neural networks, are very, very data hungry. And in NLP, we see many of the biggest advances coming from people who've created much larger data sets. So the hope is that we can be able to do this much more effectively for a wider range of problems.